Hey guys, Greg here. Today I'd like to talk about a really common data structure known as graphs. Now, if you've gone through this course, you actually have already seen a bunch of graphs. Trees are a subclass of graphs. Linked lists are also a subclass of graphs. But more general, the most general thing that you could have here is a graph. So what a graph is basically just defined as a bunch of vertices. So those are places, for example, and we have edges connecting them. So we have vertices and we have edges. Okay, so let's make a quick example here of a general graph. So maybe we were in Toronto, so I'll write this as TO. That's where I am right now. I often fly to something like, say, New York for some sort of a meetup. Now, from New York, you can go to tons of different places, pretty much most places in the world. You could say go up to the UK and Britain, which is going to be somewhere up here. And from Toronto, you can definitely go to the UK as well. And from UK, you can go back. You could definitely, from New York, go back to Toronto as well. From the UK, you could, for example, say go to something like Egypt. I don't actually know if this is true, but I'll just claim that it is. And for fun, let's say that once you go to Egypt, you actually can't come back to the UK, but you could go, for example, over to, say, India. And again, I'm just completely making this up. And from India, you could probably go to most of these places, but we'll just say, for example, to the UK. Okay, so this is an example of a graph because we have these things, which are called vertices. So this is one vertex. You could store whatever data you wanted. And then from those vertices, we have edges. So this is an edge right here. From any vertex, we have some amount of edges connecting the graph together. And a graph doesn't have to be connected like this. Maybe we had something like, I'll just have a little fun here with Bermuda Triangle, some place where, once you get in it, you get lost. Bermuda Triangle is still a part of this graph, but it's not actually connected to anything here. It's just kind of out on its own. So a vertex doesn't have to have edges, although they usually do. Now, it's a little more common in LeetCode to have a graph that looks like this, which is each of the vertices just have a integer value. So this is node 0, 1, 2, and you're generally told how many nodes that you have total. So here you can see we have 0 through 7. So we'd have basically n is equal to 8 many vertices in the graph. And just to make sure we're good on the terminology here, a single of these node things is a vertex, and you'll see it be called vertex in graph theory like in mathematics, but we'll generally in computer science just call them nodes because that's what we've been using so far, like a linked list node or a tree node. So as you can see, linked lists are a subclass of graphs because if we just took this part of the graph, well then this literally is a linked list. We also have trees because if we say looked at this part of the graph, well then this is also a tree by itself. So trees are also graphs as well. But in the most general form, a graph would look something like this, which is just vertices which connect to other nodes via their edges. Now some more terminology here. This is actually in particular what we would call a directed graph because we have particularly from one spot, we are going to the other spot. Like look at the arrowhead here. We mean 1 is connected to 2, but 2 is not connected to 1. So there is a direction on this graph. The arrow has a head. If this was an undirected graph, well then basically it would look something like this, where each connection is actually reverse direction as well. So this is an undirected graph, meaning that if we're at 0, we can go to 1, and if we're from 1, we can go back to 0. Every edge is both to and from. Now graphs could have what we call cycles, which basically means an infinite loop like this. So if we added this connection here, you could go from 0 to 3, and then from 3 to 7, and then 7 back to 0, and then 0 to 3, and then 3 to 7. This would basically form an infinite loop here. So this is what would be called a cyclic graph, meaning that there is a cycle in it, and those graphs can be difficult to deal with, and we'll learn about that when the time comes. Now there's several different ways that this graph could be stored in a computer, but the most common way would just be to be an edge list, which is a list of its edges. So this would be the edge list for the graph, and the order of these doesn't really matter, but what it is a list of edges. So this is an edge where we're saying from over to 2. So from 0, we can go over to 1. So this is marking that there is an edge here. We are marking that 1 goes over to 2 via this edge here. 1 is connected to 2. Now, along with this information, we'd probably be told that it is a directed graph, or at least told implicitly by the problem. We'd be told it's directed and that it's formed in the process of from over to 2. So they would kind of tell us that this is the structure of this. Now, if we were given this edge list, we could have also been told it's an undirected graph. And if this was the case, well, then basically 0, 1 would actually be denoting that 0 is connected to 1 and 1 is connected to 0. Now, an edge list is actually really irritating to work with because for any algorithm, as we'll see shortly, generally we're concerned with at a particular location, we're curious where we're able to go. go. Like for example, if you're in Toronto, we're curious if we can go over to, say, India or to China or to New York or whatever. We're rarely interested in the graph as a whole. That's not too interesting. So this gives rise to what is called the adjacency matrix. So it's a two-dimensional list, so a list of lists. So we have n rows by n columns. And so here we have the indices for the row, and that's basically where you're going from, and the column would be where you're going to. So for example, row 0 here, from 0, you are connected to 1 and 3. So from 0, you're connected to 1 and 3. And then basically all of this other stuff here is just going to be zeros. So if you were at node 0 and you wanted to know what you were connected to, well then you would just index this thing and look at this row and be like, okay, I'm connected to 1 as well as 3. Now let's fill out the next row here. So 1 is only connected to 2, so 1 is connected to 2, and the rest would be zeros. From 2, we actually have no connections at all, and so this is going to entirely be zeros. So from 3, we can go over to 4 and 6 and 7. Okay, so this would be the rest of our matrix here, and you can verify that that's correct. Now, as you can see, the main problem with this adjacency matrix is that we're storing a ton of information. And in fact, there's kind of a second problem, which is if you don't have any connections, why do we have to loop over this whole row to figure that out? Like if you were at 7, you basically have to go through all of the nodes here and figure out we're connected to nothing. That's still pretty inefficient. Like we would rather just like a list of nothing saying like, yeah, we have no neighbors. And by the way, I think that's my first time saying neighbors. Generally, you are talking about a node's neighbors are 1 and 3 here. Okay, so this actually gives rise to a different data structure known as an adjacency list. Okay, so this is called an adjacency list, but I actually drew it with curly braces here to kind of indicate that it's a hash map. The easiest way to do this is via a hash map where you have the key is the node's value, and its value is just a list of all of the connections that it has. So here we have 0 is connected to 1 and 3, 0 is connected to 1 and 3. Here we have 1 is connected to 2, 1 is just connected to 2. So that's what we usually work with. There is kind of one more way we might store a graph, which is via a class. So you could definitely store this as like having a class node. And so each node, for example, would have like a node.value, and it would also have a node.neighbors. So basically saying all of its connections. And that would be by default, you could kind of set it as an empty list. But if you're talking about say node 0 here, then that would have a connection of 1 and 3. And I'm actually going to draw these with circles in them to represent. You actually particularly want them to be references. You wouldn't just want to say you're connected to the values of 1 and 3. You'd actually want these as objects or class nodes themselves in memory. That way you could actually go over to those nodes. Now, generally with graphs, we do things to traverse them. And so you do either a depth first search or a breadth first search traversal. Let's start with a depth first search or DFS. And for this explanation, I want to add a cycle into the graph. So I'll put this connection right here as 4 is connected to 5 and 5 is connected back to 4. And this is done for a directed graph, although the process is pretty similar for an undirected graph. Okay, so just to first visualize what a DFS would actually do, let's say we started it at 0, so you'd have to pick a node to start at. What a DFS would do is prioritize depth. It tries to go down particular paths, and we'll just kind of output the nodes in order here. So we see 0, then we'll go over here and see 1. We'll go over here and see 2. Okay, 2. And then 2 has no neighbors here. It has nothing pointing out. And so really all we have to do is just to kind of backtrack. And so we would basically just kind of return back to the 1. Well, it did its only neighbor of 2, so it goes back to the 0. And now it has another neighbor. So it's going to go over to 3. So we'll mark down 3. 3 picks one of its connections. It doesn't really matter which one. We'll say that 3 goes over to the node of 4. Now, what's very interesting about this situation is you wouldn't really want to go over and process this 2 because we've already processed that 2 before. And if there was actually a lot of other stuff in the graph here, like maybe there was a node 10 over here and a node 9 over here, well, you would have already did that stuff before. And so you don't want to do that again. That would be very silly. And so something very important for any traversal is to have a scene set, which is going to be a hash set, which stores the nodes that we've already seen before. So it would start empty at the beginning of our traversal. And let's actually just go through this again using our scene set. Okay, so we started at at 0, so we'll kind of initialize it with seeing 0 already. Now let's go over to this and pick the path of 1. We will add 1 to our set, and we'll say that we've outputted 0 and 1 so far. We go over to the 2. Okay, we mark down that we've seen the 2. We print the 2. We would then go back here just like we did before. We go and see the 3. Okay, we'd add 3 to our scene set and print 3. We would go over to the 4, for example, and put that into our scene set and add 4 here. And then when we go over to the 2, we actually don't even use this connection. We would basically evaluate this connection. We'd be like, hey, we're going over to 2, but 2 is already in our scene set. We've already seen that. And so in constant time here, you can ask, like, have I been to this node before? Well, yes, you have. And so you're not even going to go down this connection. This edge is not even going to be used here. And so then you would go over to, say, for example, 5. We would add 5 into the scene set, and we print 5 over here. And then 5 would again say, nope, we've been to this 2 before. And most importantly here, this is what lets us ignore cycles, because if you went down this edge here, we've already been to 4 before. And so it's not going to do that again. If we didn't have this scene set and we were just going willy-nilly here, well, you'd go from 4 to 5 over to 4, and then from 4 to 5, and then 5 to 4, we would go down that infinitely. But if we keep track of nodes we've seen via our scene set, we'd actually ignore both of 5's connections here. We'd go back to the 3, we would go over to the 6, we could print that. Okay, we would go back to the 3, we go over to the 7. Sorry, I should have added that 6 in there. We'd add 7 to the scene set, and ultimately we would go back to the 3, which would go back to the 0. We did all of its neighbor connections, and so we are going to finish our traversal, and this would be the output that we see. Okay, so that was basically what would happen in a recursive depth first search. So if you use recursion to do that, now it still uses a stack because it still has a recursive call stack, although now we'll do it called an iterative DFS with a stack, which still does depth first search, although we use a literal stack data structure and we use loops instead of recursion. So what we would do is basically initialize onto the stack the place we're starting from. So we're starting from the source. Generally, you call this the source node. We are starting from the source of 0. And we'd also say that we've seen that node as well. Okay, then basically what you would do is while you have a stack, so while there's still something on the stack here, it means that there's a node we want to pop off. So there's something on there, of course. So we'd pop off the 0. And basically what you would do is you would put onto the stack all of its connections. So we have a connection of 1, so we want to put that on the stack, and we'll also add that to our scene set so that we don't add it to the stack again. And then you would add the 3 node as well. And then we'll also say that we've seen 3, so we don't add it to the stack again. Okay, then notice what will happen here. Since this is a stack, we pop from the right side, so now we're ready to process the 3, and so we actually see this a little bit differently here. Instead of going down this path, we're actually going to go over here, and it's still going to be a depth first search. It just kind of looks at it a little bit differently. Okay, so we process the 3, and then it has 3 neighbors, 4, 6, and 7. So basically what it would do is one at a time add each of these things into the scene set, and it would add them to the stack. So we'd see that we have 4 and 6 and 7. Okay, 3 has processed all of its node connections here, and so we're done processing 3. We need to pop something off the stack, so we end up taking the 7. Now there's not really much to do there with the 7, and so we would just pop that off. Same thing with the 6, it has no connections, so we would really just pop that off. But the 4, it has connections. 4 is connected to 2 and 5, and so we haven't seen either of those 2 yet. So we'd add on to the scene set 2 and 5, and so we would put onto the stack 2 and 5. It is going to pop off the 5, and so we will go down this connection here to see the 5. Well, it has 2 connections, which are 2 and 4. But notice that those are already in the scene set here. Even though we actually haven't really visited or processed the 2 yet, we made sure to put that into the scene set, because if we didn't, if that wasn't there, well then we kind of would have added this again into the stack. And you don't want that. That would make no sense. So basically, immediately, as soon as you put something into the stack, we're going to add it into our scene set as well, so that that doesn't happen. We would then process the 2, except that has no connections, so not much there. And then we would actually end up going over to the 1, which is really interesting. We basically did this path right here of these values in this order, and then the next thing is actually to do the 1. So we pop that off here, and so our stack would actually be empty, which is when we would terminate our loop. Okay, now let's see what happens in a breadth first search, and that's going to use a queue. So basically what BFS is you start at some node, and then we want to kind of spread ourselves thin here. So since 0 is connected to 1 and then 3, the first thing we'd see is 1, and then we would see 3 after that. So DFS would have said, no, you had 1 here, let's go down this path. Or maybe if you went over to the 3, we would end up kind of in its path over here. But it's a BFS, so we'll see the nodes in order. So we have 1, and then we see 3, and then 1 was neighbors with 2, so we see that next. And then we're going to see all of 3's neighbors, so we see 4, and then we see 6, and then we see 7, and then 4 was connected to 5, so we'd see that. BFS is about spreading yourself thin, and so we go here, then here, and then here, and here, and here, and here, and then here. And a DFS would have done something like this, where we're like, no, let's take a path, or like, let's take a path like this. So BFS uses a queue, and so you would basically initialize your queue with the thing you want to start at, which is the 0. And then basically you would do exactly the same thing as the iterative DFS with the stack, except you will pop from the left side. Okay, so there's something in the queue, so we'll pop off that node. Okay, so we have processed the 0. Well, it is connected to 1 and 3, and so we want to see them in that order. We want to see 1, and then after that we want to see 3. And we'll place both of those in the scene set to make sure we don't add them into the queue again. Okay, so now we are ready to process the next node. We pop from the left side because it's a queue, so we process the 1. Okay, so we visit the 1 and we see it's neighbored to a 2. So we're going to add that 2 into the scene set, and we're going to add that after the 3. So we want to make sure we visit the 3 before we see the 2. That's exactly what it allows it to do a BFS. Okay, so then we would process the 3. So we're seeing this guy right here. The next thing we want to see is the 2 because we saw it from 1's neighbors. So we want to see a 2 before we see the 4, the 6, and the 7. So we'll add all of those into the scene set, 4, 6, and 7, and we will add those into the queue, 4 and 6 and 7. Okay, so the next thing we process is the 2. So we'll pop that one off here. We will see that it is neighbored with nothing, so there's not really much that happens here. The next thing we would do is process the 4. So we see the 4. Okay, it is connected to a 2 and a 5. However, we already have 2 in the scene set, so we're not going to add that one in here. We don't want to go down that path again. We do want to see the 5 though, so we will add 5 to the queue. So we want to see that after all of these guys. And now we're done processing 4. Okay, we are going to see the 6, and there's not really much to do there. That basically just pops off and does nothing. We are then going to see the 7. Okay, we see the 7. That one comes off. That basically just pops off and does nothing. And finally, we would process the 5. We take that out and process that. We'd see it's connected to 2 and 4, but both of those are in the scene set, so we don't add that. So that is what would happen with a BFS, and you'd particularly use a queue for that. Okay, so let's talk about time and space complexity for these algorithms, and we'll kind of assume that we're using an adjacency list. It does kind of depend on how you're storing the graph, but we'll assume that we're using an adjacency list because that is the most common. So the time complexity here, basically what we're doing is for every single node, we are taking all of the edges that it has, and we were seeing all of those other nodes. So we're seeing all of the nodes, we're obviously seeing all of those guys, and for each of those nodes, we're seeing its neighbors. Now, generally when we describe these things, we do it in terms of V and E, where V is the number of vertices, we've also been using N for that, and E is the number of edges in the graph. Now, some of you might be tempted to say that the time complexity is big O of V times E, and that would mean that for every vertex that you have, you're visiting all of the edges in the graph, but you're not. What you're doing is you are visiting for each vertex, you're seeing each of its edges. So you're not seeing all of the edges per one vertex. For one vertex, you're seeing its edges. So this is actually a V plus E. We are seeing in total all of the vertices, and you're going to see all of the edges. And that's true whether it's a depth first search or a breadth first search. It doesn't really matter which one it is. So the time complexity of this is going to be V plus E. And the space complexity, what we're storing, well, again, we'll assume that this is an adjacency list. And so if you are storing that adjacency list yourself, well, you're storing all of the vertices because those would be the keys, and you're also storing all of their edges, and so that's again a V plus E. If you were doing this with recursion, you could technically have it like a linked list where you're just going like all the way through all the nodes. That would store space on the recursive call stack, but that would again just be in the depth of V. And also you are storing a scene set as well as either a stack or a queue. All of this stuff here, you're placing vertices on them. So again, you're basically just storing vertices. These are all just going to be reasons you're storing V things. So the space complexity of a breadth first search or or a depth first search, both of those would be v plus e in both time and space. Now I wanted to finish this lesson off with particularly explaining what trees are in the context of graphs. So basically, if you had something like this, we'll say 1 goes over to 2, and we'll do this as an undirected graph, although it doesn't really matter. 1 goes over to 2, goes over to 3, goes over to 4. This is an example of a tree. And you would know that because if you basically rotated this 90 degrees, you would see this guy as the root, and we're going over to his children like this. So this is a tree. You know what's not a tree is something like this. This is not a tree because it has a cycle. So a tree is what we call a connected, we'll explain that in a moment, and it's an acyclic graph. Okay, so acyclic means no cycles. So it's connected with no cycles. What connected means is from anywhere in the graph, you can get to anywhere else in the graph. So from this 4, you could get over to 3, to 1, and to 2. You can get anywhere. From the 3, you can get to the 4, and the 1, and the 2. An example of an unconnected graph would be this one right here. This is not connected because from this 1, you can't get over to the 5, and if you are at the 5, well then you can't get over to anybody. So this would be unconnected, so it's not a tree. So a tree is a connected and acyclic graph, which is like this. It is a connected graph and it does not have any cycles. If you had something like this, this would generate a cycle and it's no longer considered a tree. Now there's something pretty cool about trees, which is that if you have n nodes or v vertices, either one is fine. So if you have n is equal to 4 nodes, well then you'll particularly have e as n minus 1, which is equal to 3. Why is that? Well, if you have a connected acyclic graph, well it means that you can get from one place to any other place, and it means that there's only one way to do that because it's acyclic. If there was a cycle, say something like this, well then there's multiple ways for 3 to get over to 2. We could go here and then here, or we could go like this. So if a tree is connected and it's acyclic, you can get anywhere with no cycles, well then you're going to have particularly one less edge than the number of vertices. If you added any edge here, that would cause you to have the same number of edges as vertices. That means by definition there's multiple ways to get somewhere, which means there's a cycle. And if you had less than n minus 1, so let's say 2 edges, well how are you going to connect all of these things up here? You could do this and then this, but then this guy's not connected. You could do this and this, you could do this and this. No matter what you do here, someone is going to be missing because you have 2 more vertices than you do have edges, so you won't be able to connect everything together. So that's why you particularly have, if you have n vertices and you are a tree, that means you're going to have n minus 1 edges. Okay, so this is the graph we'll be working with for the most part. Note it is a directed graph, and I'll show you how to make changes for making it undirected when the time comes. Okay, so generally we are given some array of edges, not always, but most of the time. For now, we'll assume this is directed, and so usually we've been told how many nodes we have total, so n is equal to 8, for example. And so maybe we are given this array of edges, we'll call it A. So let's say it looked like this, where we have a bunch of different edges here, and this first connection says 0 is connected to 1. We'll assume that this is directed for now. So we'll assume this is basically from the start point over to the end point. So this means that 0 points over to 1 and 1 points over to 2, 0 points over to 3, and so on. You can actually see that in our picture right here. So again, it's just implementing that graph. So all I'll do for now is just output this. And so if you have an array of edges, one thing you might want to convert it to is an adjacency matrix. And so this is how to convert an array of edges to an adjacency matrix. So we'll call our matrix M, which is just going to be an empty list for now. And then we'll do for I in the range of n. So if we have n vertices, we would want this to have n rows and n columns. So n times, we're going to make a row that has n many values. That makes an n by n matrix. And for now, we can just see that it's empty here. We have n by n zeros. Then what we'd want to do is for each u and v in the graph, which is A. So for each starting vertex u and ending vertex v in our array of edges, you'd want to set the matrix at u at v equal to 1. This specifies that at row u and column v, it is a 1, saying that u is pointing over to v. If we are to output this, you will see, for example, this here is the first row. So this is all of the connections that node 0 points over to. So we see that node 0 points over to position 1. That is true. Node 0 points over to position 3. So this is 0, 1, 2, 3. That is true. It also points there. Now, if this graph was undirected, you would want to just specify the opposite connection. So you would uncomment the following line. You would set m at v at u equal to 1. So if we are to do that for a second here, we will see that it's actually what's called a diagonal matrix. So you can see here across this bottom right diagonal, you see these two are both 1s. We'll see that both of these two are 1s and these two are 1s. A little hard to see, but it's just the opposite connection. So we'll keep it as undirected, but if you wanted it undirected, then you would specify the opposite connection as well. Now, to be honest, I'm not sure if I've ever really worked with an adjacency matrix. I often prefer to work with adjacency lists. They're usually more useful. So here's how to convert an array of edges into an adjacency list. Now, there's multiple ways, but the easiest is from collections, we'll import the default dict, which is just a cool dictionary. So we'll set d equal to a default dict, which takes a list. So it makes the default value for a key be an empty list. Now we'll say again, for each u and v in the array of edges A, you would just want to specify that the dictionary at u, we have one more connection, which is going over to v. Okay, so if you did that and we outputted d here, you would see, just to look at this piece right here. So we can see that 0 points over to 1 and 3. If we go up here, we will see, yes, that 0 points over to 3. It also points over to 1. So that is both of its connections. We see that 1 points over to just 2, 3 points over just to 4, 6, 7, and so on. It's really, really nice. What is node 3 connected to? It's going to precisely tell you it's connected to 4, 6, and 7. Whereas if you wanted to do that with the matrix, if you said m at 3, so what is node 3 connected to? Well, it's kind of awkward. You'd have to kind of go over this array and see that it's these positions. Whereas d at 3, that just tells you immediately it's connected to these ones. Okay, and similarly, if you wanted to make this an undirected graph, then it's really, really easy. All you would do is uncomment this line. You would d at v dot append with u. So we're saying v has another connection of u. Now, if this really didn't make any sense with the default dict, I encourage you to check out the end of my hash maps video where I talk a lot about dictionaries, default dicts, as well as counter. Okay, so it's usually with this default dict that we'll end up performing our code on. So the first thing we'll do is a depth first search with recursion, which as we saw has a time complexity of the number of vertexes that we have and the number of edges that we have total. Okay, so we'll say we're doing this from the source of 0. We're starting our search out from 0. We would need a scene set, which is going to be global to the function, so an empty set. And we'll say that we've already seen the source. Now we'll write this function in a second, but what we'll do is call a function called DFS Recursive, which takes a node. We're starting it at the source. Okay, so I'll make room for my function up here. So we'll define our DFS Recursive, which just in general takes a node that we're currently at. We're just starting it from the source. And its main function here is just to print the node. So this is just to see the order. In general, this is kind of your processing here. And then we say for each neighbor node in the dictionary at the node. Okay, so we're at this node. We want to one at a time go through each of its neighbor nodes. We only want to go there if we haven't seen it before. So if the neighbor node is not in the dictionary of seen, well then we want to go over to it. And the first thing we'll do is mark that it's in the set. So we'll say, okay, we have seen this. We are actually going to go and see this right now. So we'll just say that it's in our set and we'll immediately go to that neighbor node. So DFS recursive on the neighbor node. So what this is going to do is a depth first search, and we can actually run this. We will see 0, 1, 2, 3, 4, 5, 6, 7. Okay, now let's do an iterative depth first search with a stack. So it'll do a DFS, but it's actually going to visit the nodes in a slightly different way, and you'll see that. Okay, so let's set these same things up here. You would still want from the source of 0 and an empty hash set of what we've seen. We'll say so far we've seen the source. Then we would want a stack. So we'll set a stack equal to the list of just the source. So that's what we want to visit first. And then we would do while we have a stack. So while there's something in the stack, we want to pop off a node. So we would do that. Node is equal to stack.pop. And this is what we're currently processing. So we'll process it again by just printing that node. Then this part is almost exactly the same. For neighbor node, in the dictionary at the node. So for each of the neighbors that it has, we only want to visit it if we haven't seen it yet. So if the neighbor node is not in seen, then you would want to visit it, and we'll mark immediately that we have seen that neighbor node. And then we put it on the stack. So stack.append the neighbor node. Now, since this this is not doing recursion, it's actually going to complete this for loop by putting everything on the stack, and it's not going to just immediately from one of the nodes jump into the function on that node. It does it in a stack. It goes through this loop and puts those values onto the stack. So when we actually run this here, we still get a depth first search, but it's 0376451. Okay, now let's do a breadth first search, which would use a queue. Again, that's going to have a time complexity of v plus e. So we would still do it from our source node of 0, but now we need a queue. So we'll from collections, we will import the dq object. And very similarly here, we would still get a scene set, which is empty. We will put on that we've seen the source. We would get an empty queue. So q is equal to a dq. And the first thing we'd want to visit is the source. So we'd put that on the queue. This is going to be very, very similar to the iterative stack version. And I'm going to copy that so you can see just how similar it is here. So to make this a breadth first search, it would use a queue. And instead of popping off the node, which this pops it off from the right, you would want to, from the queue, pop off from the left. So we're still going to append on the right side here, but we want to pop it off from the opposite side. And that's actually all the changes that we have to make here. So if we run that, we'll see 0132465. Okay, now there's one more thing I want to do in this lesson. And to be honest, there's endless graph theory that you can do, and we'll see most of that in the problems that we solve. So I'm not going to bother doing it now. But I'm making a class here because you can also store graphs in memory as objects via a class, similar to how we did trees and linked lists. Trees and linked lists are just a subclass of graphs. So of course you can make a general node class as well. So we'll just set the self.value equal to the value. And by default, we'll set its self.neighbors. So this is all the stuff it's connected to. It's going to be a list of other references to other nodes. But for now, we'll just have that empty as a default. We'll give it a string method, which is how it's going to print itself. And we'll also give it a function called display, which is just going to get a variable called connections, which is each of the node values for everything that's in its list of neighbors. And it's just going to say that that node is connected to its list of neighbors. Okay, so then to create an example graph here, you would just make some nodes. A is going to be a node of A. And here we're giving them string values, which are basically names, but those again could store really any data you want. And we'll just make a few more of these here. So we'll make a node B with the value of B, C with the value of C, and D with the value of D. Then we need to give them some neighbors here, and I'll just kind of copy some in here. So we're saying that A is going to have another neighbor of B. So notice we passed the reference of that object in here. So A is now neighbors with B. B is also neighbors with A. C is neighbors with D, and also D is neighbors with C. So it makes a very simple graph here, and we'll just use our display function a few times here. If you display A, you'll see it's connected to B. If you display B, you'll see it's connected to A, and you could do that with C and D as well. Okay, so as always, you can check the video description if you want this code. I hope this was helpful, guys. Drop a like if it was, and have a great day. Bye-bye.